Hi folks, we need to make this heat sink out of aluminum. Relatively simple part. So why watch this video? Well, 3 reasons. Number 1, we're going to compare adaptive tool paths. Which is faster, a 1/4 inch tool or a 3/16 inch tool? Number 2, we're going to talk about getting this fillet looking really nice as we walk around that edge. And number 3, if you're always wondering about flipping parts over to get that second side or third op done precisely, we're going to dive into that as well. Welcome to another Wednesday Widget. Cutting up some aluminum on the Dewalt Saw. Again, we love this saw and we love the plate that we make for it. It helps make reliable cuts that are safe, pretty free of burrs, cold to the touch. It's a win for us. We need to set up 2 tools for this job. The first one is this guy. So what is this guy? It is a Lakeshore Carbide corner radius end mill. Go to lakeshore.com and click corner radius mills, 2 flute, 3/8 inch. And this is the one with a 60 thou radius. We can do this with the ball end mill as well, but we get much better tool pass out of this corner radius end mill. And the other tool we've got to set up is a 3.5 millimeter drill. We really like these Hoyt bins. Tormach actually has a really good price on these. They're a little expensive, but boy, I don't regret buying them. Once you've got them, they are great to have and to organize your tools. If you notice that set screw looks a little different, on our video, Speeds and Feeds, the basics, getting started, we talk about replacing that set screw. It's one of the best upgrades you can do to your TTS set screw holders. 3.085. Touchscreens are a must, in our opinion, on the Tormach. It's not only faster, it's actually safer, in my opinion. When you're using a keyless chuck or an Albrecht style chuck, you never seat the drill or tool all the way at the bottom, because as you tighten that chuck, it wants to pull it in a little bit. So you need to allow for some room for that tool to travel. 5.431. After about a year in the works, we're getting up content on the nyccnc.com website. Under What to Buy Tormach PCNC, we've got an Excel file, free, that lists all of the recommendations and advice, including these racks that we really like to hold tools. We modify them a little bit, but check out that list to find out these. They're relatively inexpensive and it's a great place to store your tools. I still do all my Fusion programming either on my laptop or at home or on my desk, but it's great having a shop computer. You can do your final looks, final setup sheets, and post out. Notice our work coordinate system, top left, post. All right, using the Heimers, find our Z0, and then we're going to come over and find our X and Y. And again, the touchscreen is what makes this so easy to set between your units. First op is the Superfly. We're just taking a quick skim cut here, 2,500 RPMs, about 15 inches a minute. We're going to push it harder. We've been experimenting with how do you get the best material removal rate and surface finish. I bet we need to tram this head in. We're not quite seeing as good a finish as we've seen before, so stay tuned. That's another video we want to do, is maintaining and tramming in your Tormach. 2D adaptive, shear hog, all the RPMs you've got, 10,000 of them, 60 inches a minute. That's 6/1000 of an inch feed per tooth. 0.15 inch width and 0.15 inch depth of cut. That's about 3.8 millimeters width of cut and depth of cut at about 1,500 millimeters per minute for the folks in the rest of the world. Time out. We've got our traditional 3 flute 1/4 inch end mill. The task at hand, adaptive out this slot, which is 0.3146 in diameter. It's about 8 millimeters. What do you think is going to be faster? A 1/4 inch tool or a 3/16 tool? Any guesses? So we threw the time up here. The 1/4 inch tool took 2 minutes and 49 seconds. One of the reasons we want to do this test is that the machining time in Fusion is a great tool, but it gives you a relative time, meaning the machining time isn't always going to be correct on certain machining options. In this case, the problem is the acceleration and deceleration of the machine. Fusion isn't even close to being able to take that sort of thing into account. What you can see from Fusion is that it thinks that the 1/4 inch will be faster, 43 seconds, relative to the adaptive at 1:22. The opposite ended up being true. We broke the 3/16 tool, which you're going to see here in a second, but we ran it again to confirm that it ran in 1:52 seconds, almost a full minute faster. And the difference is that with the smaller tool, it's able to make longer moves where it's able to spend more time at maximum speed rather than smaller moves where it's spending more time accelerating and decelerating. And in fact, it may never accelerate to the desired feed rate. Our 3/16 recipe, 10,000 RPMs, 40 inches a minute. This is the recipe that we used after we broke this tool, which you're about to see, and it was much more reliable. And so why did we break this tool? 4 possible reasons the tool broke. Number 1, too much width of cut or optimal load or radial engagement. Number 2, poor chip evacuation. Number 3, if the part itself got hot. Number 4, lack of a coolant blowing on the part providing a lubrication. Whichever one it was a result of the fact that aluminum is gummy and you have to evacuate the chip, and if you don't, it will start to chip weld, and that's what ultimately happened here. So we do like using these tools. A lot of times we are able to actually squeeze the aluminum chip and have it sort of peel out and not damage the tool, but we need to take a closer look because a lot of times you are going to compromise the cutting edge of the tool. Was it damaged, or is there some aluminum left that could be a built-up edge that'll cause it to chip weld again more quickly? So 3 ways to do that. The most inexpensive way is this. Link here. This is $5 to $10 on Amazon. It's a 45X pocket loop. Just absolutely great. The 2 better options are this, which is a little USB benchtop microscope, which I really like. It's about $100. Or you can go up to a big boy microscope. This is about $800 to $900. Let's take a look though. The benefit of this one is it's easy for me to show you guys on a screen, and it's what we've been using every day. For example, trying to read this boring chip that came off to get an idea of how the chip formation and the heat is, take a look at the quality. So there's a tiny piece missing on the very corner of that flute, but the other 2 flutes are pretty chipped away. You can see the edge of the corner is missing right here. And likewise, this one is missing. But if we roll the tool over and take a look, you get an even better idea of how the carbide fractured. And I'll be honest, a lot of times I'm able to recover the tools a little bit better than this. I did let this one chip weld a hair longer, and sometimes you break it when you pull the material out. Now, do we need to replace this tool? Yeah, we do. You could probably put it back in the machine, and I bet you it wouldn't be that bad. So if you were in a pinch or your only tool left, this isn't beyond total failure, especially since we're leaving some stock to leave in this adaptive, but we're going to replace it. So we need to rerun this adaptive, and I don't want to waste all that time. Model. Sketch. Create sketch. I'll pick this plane right here. Now I need to hit P for project to project that floor in. That's because we have a setting changed under preferences, which is to not auto project our sketch. That's how we enjoy using Fusion. If you want to see how we do our preferences, go to nyccnc.com, click Learn Fusion 360, and we've got a whole variety of Fusion 360 tutorials. And under our Getting Started with Fusion 360, we've got our recommended preferences and settings video that walks through that. So now that I've got that sketch, I'm going to toggle off the component visibility just so you can get a better idea. And what I'm going to do is hit L for line and sketch a line that forms this box, D for dimension, and looks like the caliper show it's about 0.56 inches, so we'll just round up to 0.65. That gives me an area that I can select as our stock. So take a look at this. Go back into CAM. That adaptive, right click, duplicate. I'm going to rename it temp. That's what we do in our shop, just because if we save this file and run it later, we want to make sure we don't normally run that op. Right click, edit, and under geometry, stock contours, delete what I currently had selected. I'm going to pick that box. See, it's tricky to pick, so let's do this. Let's hide our component, and let's try that again. You know what? I think we've got to edit that sketch to delete the other items. It doesn't like the mix of projected and sketch lines. So I'm going to right-click on that sketch, edit sketch. And this is something I really want Autodesk to improve, which is right now I can't delete just a portion of this purple line. The technical term is that it won't accept partial projected sketches. In other words, this purple line is linked back to this solid model, which is cool because if I update the solid model, the purple changes. But I want just sort of a portion of the purple. And if you notice, if I go to Sketch, Trim, I can't trim it right now. So what I've got to do is select everything, right-click, break link. Not a big deal here, but now it's not parametric, which is a bummer. But now what I can do is Sketch, Trim that away. I lost that bottom line, no big deal. I'll put that back in. Now I want to lock that in place, so I'm going to drag a box around everything and choose Fix. It'll go green, which means I can't move it. Toggle my component back on. I was going to say toggle it back on to make sure it didn't go anywhere, but that's exactly why we do that. Huh, look at that. Interesting. So let's do this. Before we delete the stuff, let's fix that. See if we can trim it now. Interesting. Looks like that worked. Stop. Okay, now it's in the right place, and it's green. I can't move it around. Great. Go back into Cam. Pick that. So we've got these two chains selected, the red line here and the red line here. So it sees all of that area as geometry for the 2D adaptive. But what we've also done is told it, hey, you only have stock, meaning material to work with, in this new rectangle right here. So that's what it focuses on. It says, hey, I could do work everywhere, but I'm only going to do work where there's material to remove. So if we click OK, now it's going to run our toolpath just in this area here. Obviously, that was a fair amount of work for what was only a 45-second operation, but this could be a really big deal if you've got a long adaptive and you need to stop it midstream. After our adaptives are done, we do a horizontal cleanup to clean up that floor. And then remember, adaptive is not a finishing strategy, so we're using 2D contours to walk around the slots, the profile, and the overall outside shape of the part. Spot drilling. For years I spot drilled way too slow. We're using Carbide spot drills. You can push them down pretty quickly. This was 150 surface feet per minute, or about 3,000 RPMs, and plunging at 24 inches a minute, which is 8 thou per rev. Drilling at 5,000 RPMs, which is about 180 surface feet per minute, and that's my general recommendation when you're getting started with aluminum or even steel, is somewhere between 100 and 200 surface feet per minute. And we're feeding at about 8 thousandths of an inch per revolution, or about 0.2 millimeters per rev. So here we go, walking around this part to get that edge fillet. I spend a fair amount of time playing with this toolpath, and it's a great example of one where you may just want to copy and paste it into your next file to avoid having to figure out or remember all of these settings, or you can put it in as a template. But again, we're using that 60 thou bullnose end mill, and under geometry, we don't have anything selected as the machining boundary. We have chosen to use slope. We're adding some model surfaces, so this goes back to last week's Fusion Friday with talking about how we use the patch environment to get a better toolpath. We're using touch surfaces, and most importantly, we're using contact point boundary. That contact point boundary is the biggest differentiator. Take a look. If I duplicate this, and on the next one I turn it off as a demonstration, you'll see how much different that toolpath looks. You'll see how it's making these odd motions. And remember, you want a toolpath that looks smooth, that looks like the machine is going to be able to handle it in a very fluid manner. And this turned out great. I was really happy with this quality of this edge. We finished all of the top side. We need to flip our part. So take a look. When we did the top operation, the stock was 3/4 of an inch high and it was offset 0.02 inches from the top. So it looked like this, and you can see the 0.02 inches of stock at the top. We need to flip our part, and I want to try to maintain accuracy. So I want to stack the deck in my favor. So rather than worry about whether our stock was exactly 0.75 inches in the real world, here's what we're going to do. We're going to use geometry that we made. In this case, this face right here. We can rest that on the top of our jaws. So what I want to do is set that as my Z0. Now it's still important that we model our stock correctly, mostly so that we ensure we take the correct numbers of depths of cut. So I've got the same thing. It's 3/4 of an inch high stock, and I've got it set this time as offset from the bottom of 0.02 inches. It's actually not super important to have that correct because, again, this won't affect our accuracy so much as it will affect us making sure that our facing cut takes the correct depths of cut. We don't overload the tool. How did we get that coordinate system on that point? Hop back into Model, Sketch, Create Sketch. I'm going to create a sketch on that plane. P on your keyboard for Project. I'm going to click that plane once. Notice I'm not clicking the line or the line here, but rather this plane. And that projects every piece of geometry on that face or plane onto this new sketch we just created. Click OK. Now I'm going to hide my component to make this easier to see that projected sketch. You can see I've cheated. I've already got the point there, but let's recreate it. L for line, draw a line across. Now this alone is enough, but if you weren't sure, you could draw another line here, letting it snap to confirm that that's the intersection. You don't need that because, again, Fusion can detect what we'll do here is say point. I'll put a point in the wrong place and then use a midpoint constraint. So I'll click midpoint, click the dot first, or the point first, and then click the line. It snaps it to. So that's a sketch point. That would work. I find it's easier often to say construct point at vertex, and this creates a piece of construction geometry. That's a point. So again, the difference is that that point we just made lives in this construction point world, not in the sketch world. So if I turn the sketch off, but leave the point on, you can still see that point in there. Just a little bit easier. Fusion tends to like construction points in my experience. So hop back into Cam, and under the bottom, Operation, Edit, selected point. Ironically, it's called a sketch point, but it will accept the construction point as well. So again, I'll make sure it's turned on in the Cam environment. Pick it. Every once in a while, I've had Fusion act funny on me. So sometimes it doesn't want to pick that point. So click another random point, not what I wanted, but now I can go back and choose the point that I actually wanted. So I'll make sure you click point here first, select that. And if I look, you can see it's got that point selected in the middle of my part, right on the plane that I want it to be on. Now, I don't really care as much about the XY position. Approximate is fine because all we're doing here is we're facing it. And once we face it, we'll have exposed enough geometry to where we can better locate our XY0 and do an outside chamfer. Pushing the Superfly a little bit harder here, the same RPMs, but 28 inches a minute with 70 thou depths of cut. So we've decked it off, and what that's done is it's exposed our edges, so we can now use those edges to locate the XY of the part accurately. So let's set up this last operation. I'm going to right click on my bottom and say duplicate. And we'll rename this bottom chamfer. So what I want to do is walk around that part. First though, let's set up our work coordinate system and our stock. We don't have this big chunk of stock left anymore. So I'll go to edit, stock, and this isn't that important. The quick way would be relative size box, no additional stock. That's going to give you something a little bit closer, but really that's not accurate anymore either because we don't have these corners here. I honestly don't worry about that at this point very much. All I care about is walking this chamfer around. So I'm not relying on the stock as Fusion sees it. One other option that would be a little bit more accurate would be to edit stock and to say from solid. And I could now pick that, click OK. Either way, what I want to do is go back and edit this and edit my work coordinate system. So because we duplicated the prior operation, it's still located right here. Now the Z is okay. We could leave it there because our part hasn't moved, but let's move it to the top plane just for the sake of exercise and practicing how we flip parts. Click this X here to delete our existing work coordinate location. And I'm going to change the origin from selected point to model box point. Model box point puts a grid of dots, 3 in the Z, 3 in the Y, and 3 in the X. So we've got this grid of 27 points. You see one extra one here in the middle because that's our construction point. So let's turn it off so it's not as confusing. So we've got 9 on each kind of plane, if you will. I want this one. And if we look and orbit around, you can see that that's centered left to right and front to back in our model. That'll let us use our Heimer to find the left edge and the right edge and divide it by 2 to find the center point in X, the same in Y, front edge, and the back edge divided by 2. That gives us our XY center. And the Z I can use with the Heimer as well by probing down on the top of the part. This is how you would do it if you had to do a new op on this part that say somebody sent in for a quick repair on this back side. Click OK. And I'm actually going to take our top model, right click on this chamfer right here, say copy, collapse this. Make sure the bottom one that we're editing now is active. Right click, paste, and that moves it into this bottom op, which is nice because it brings my settings over. Edit, geometry, delete that, pick this chain, and let's move a little bit quicker here. We can easily go, say 650 surface feet, and 2,000 per rev is good. So that's 60 inches a minute. We'll see how that chamfer quality looks. Passes, just a real light edge break chamfer of 0.003 of an inch. Click OK. Let's finish her up. Finishing it up with a quick edge chamfer. Folks, thanks for watching. We love what we do when it comes to not only just CNC, but Fusion 360, the speeds and fees, and tying that in with operating a machine shop and the business and entrepreneurship side. That's our focus for 2018, is to build out even more of the content that we've got on the NYC CNC website. So be sure to check that out. Otherwise, take care. See you next Wednesday.